Hello everyone, I'm Ludovic, and this is our work, Groove, Flexible Metadata-Private Messaging. There's been a lot of recent interest in metadata-private messaging. We have all these messaging systems that provide end-to-end encryption, so the contents are protected, but sometimes it is already sensitive to know the source and destination of a message. On the slide, you see an example where Alice is contacting her abortion clinic, but in general, there is a ton of prior work showing how this metadata can be sensitive. In this system, sensitive metadata could leak in two ways. First, the servers obviously know with whom Alice is talking, but also a network adversary could correlate the time and sizes of messages to understand whom is talking with whom. So this is the problem we'd like to solve. We'd like to build a communication system for text messages that does not leak such metadata. Of course, we aren't the first one to work on the topic. At a high level, we can identify three broad categories of solutions. There are solutions based on Tor, but they do not resist traffic analysis. You have solutions based on private information retrieval, which do resist traffic analysis, but they scale less. And finally, we have solutions based on mixed-net with circuits, which both resist traffic analysis and scale better, but they don't support asynchronous clients such as mobile phones. To expand on this last point, to contribute to the global anonymity set in mixed-nets, clients need to be always online to participate in every round of the mixed-net, so they must be online and send cover traffic at a fixed rate. So this is costly in general, but especially so for clients on smartphones. The client must be always online and sending cover traffic at a fixed rate, so this immediately raises concerns about battery life and bandwidth usage. But also, mixed-net are not really designed for storing messages, so if the client is offline, these messages cannot be retrieved. Taking a step back, all these requirements are fairly different from the standard user experience with standard messaging apps. So our system, Groove, is a mixed-net with circuits, and it's all about turning this last no into a yes, enabling asynchronous clients such as smartphones for mixed-nets. In Groove, we remove the rigid synchronous requirement of large-scale mixed-nets from the related work, so users don't have to be online at the same time. This is the focus of this talk, and users can have multiple devices. Compared to the related work, it better supports mobile devices, more of this in the eval, and we do so by introducing new techniques, non-interactive circuit setup for multiple devices, a new oblivious protocol to avoid downloading the cover traffic from the mixed-net, and a new key rolling mechanism to provide forward and future secrecy for metadata. So we consider a honest sender and a honest recipient talking through our system Groove against a global active adversary who observes all network communication. He can edit, drop, delay, inject any message, and he controls a fraction of the servers. The security notion that we target is unobservability. We want that the observations that the adversary can make to be roughly similar, whether Alice and Bob are friends and exchanging messages, or they are not friends and they are just two random honest users of the system. More precisely, Groove achieves differential privacy. So at its core, Groove uses a large-scale synchronous network similar to that of the related work. We implement one, but the design is fairly agnostic to the mixed network, and as such, Groove might benefit from future improvement to mixed nets. To bridge between the synchronous mixed network and the asynchronous clients, we are going to introduce service providers. They interact synchronously with the mixed network, and users can buffer messages at the service provider and then disconnect. As said in the model, the adversary controls any fraction of the server, up to a fixed percentage, so we cannot possibly trust this one service provider, and the challenge is going to make this service untrusted. To explain how Groove works, I have two brief background slides on circuits. A circuit is a long-lived connection through a set of servers through a mixed-net that connects a sender and a recipient. The path is chosen by the sender, and once set up, it carries messages at a constant rate. The reason why circuits are useful is, once set up, they resist active attacks. If the adversary drops Alice's message, the first honest server on the path is able to fill in a message, and on the recipient side, things will look the same. The key here is one setup. And in previous work, this setup was interactive between the two participants, between Alice and Bob. They both needed to be online for this setup phase. So the first thing we do in Groove, and I have to stay fairly high level here, is we make this setup non-interactive. We make it safe for just Alice or just Bob to perform this setup phase. More details on this in the paper. But now that it is non-interactive, Alice is able to pre-compute these circuit setup messages, say for a month, upload them to the service provider, which can replay them as needed. The question is, now that Alice gave these messages for a month to the service provider, how can she contact someone else during this month? And naively, she could periodically re-upload these circuit setup messages for the next month, potentially changing the endpoint of the circuits. But there is a problem with this approach. The issue is that the service provider is malicious and keeps both versions of the messages, all versions of the messages. Let me give you one example of an attack which illustrates many of the attacks that the service provider could do. Let's say on day 2, Alice did not change the destination of a circuit. So both the old and the new circuits are connecting to Bob. What the service provider can do is replay both messages to establish 2 circuits, and Bob might be the only one who gets 2 circuits, an additional circuit. This might help him confirm that Alice was talking with Bob. So how do we fix this? To solve the problem, in Groove, we introduce safe message replacement. It's based on 2 insights. The first is, in Groove, circuits are independent on the correspondent, and for a given epoch, the paths are chosen using a fixed pseudo-random value for this epoch. So for a given day, a device is always going to pick the same path again and again. If Alice changes the destination of the circuit, it will be the same path. And if another of Alice's devices shows up and tries to establish some circuits, same path again. How does this help? Well, second insight. Per the mixnet assumption, we have at least one honest server on the path from Alice to Bob. The reason for this is that the adversary controls up to a fraction of the servers, and we pick sufficiently long paths through this mixnet to be sure that there is a honest server on the path. See the related work and the paper for more details on this aspect. But the insight is that although the service provider is malicious and quite powerful, we can rely on this honest server on the path to uphold the security properties of the system. In particular, to prevent the attack I presented 2 slides ago, this honest server can deduplicate the circuit setup messages and ensure that there is only one circuit from Alice to Bob. This differs from the related work, which uses truly random paths for each circuit setup, but this does not allow to deduplicate. So this is what we call primed circuits. It is the combination of the non-interactive setup for circuits plus the technique for safe message replacement. And this drastically changes how Alice interacts with the mixnet. Now she pre-computes all these dummy messages in advance, upload them to the service provider, and then at any time, irrespective of the schedule of the backend, she can change these messages with actual recipients or actual contents. So that's how we achieve asynchronicity. And as said, these rely on the honest server that exists on the path between Alice and her recipient. Following this insight, we also have other contributions, which I'm only going to briefly mention. The system supports multiple independent devices from one user, even if they cannot coordinate. I'll briefly mention this. Clients don't have to download all the noise messages that are generated by the mixnet. They can select a subset of messages of interest. And finally, we have a new key rolling mechanism to provide future and forward secrecy for metadata and to prevent one old device from compromising new devices. But I'd like to show you how this works. So we implemented the system in Go in 20,000 lines of code on top of Yodel's mixed network. We use TLS 1.3 for transport security and gRPC, and we build an Android client using Go Mobile. We have more eval questions on the paper, but I'm going to focus on the client side here. And we're going to see what is the end-to-end latency of the system, what is the phone bandwidth usage, and what is the energy consumption on the phone. The experimental setup is as follows. We have a client on a Pixel 4. We use 100 servers on AWS between 4 different regions in Europe and in the US. Each server is a fairly powerful machine, and we simulate up to 3 million users, each with 50 friends. So first about the latency. The latency, the end-to-end latency of the system is between 32 seconds and 2 minutes from the user's perspective. It has 2 components. First, it's how often the client decides to connect to the service provider. And here in this example, it's 1 minute, but this is chosen by the user. And then the backend processes messages in 32 seconds for 1 million users or 80 seconds for 3 million users. Second, we want to have a look at the bandwidth usage. The phone uses about 100 megabytes per month. Circuit setup messages are fairly small. And then for a phone that connects to the service provider every minute, messaging is around 103 megabytes per month. We deem that this is fairly acceptable since, at least in the US, most mobile data plans are in the gigabytes. But as a point of comparison, many related work rely on a system called Alpenholm to perform a similar functionality. And Alpenholm, when deployed in our setup, would use 62 gigabytes per month and per device. Finally, I want to compare the battery usage to that of an idle phone, screen turned off for the duration of 1 hour. The x-axis is the duration of the experiment, and the y-axis is the extra energy spent by the phone. The curves are examples of schedules chosen by the client. First takeaway, on cellular network, fast schedules drain the battery. So if you were to deploy the state-of-the-art, such as Karaoke or Vuvuzela, on a phone with this configuration, you'd kill the battery probably very quickly. Second insight, on Wi-Fi, even fast schedules have a much more reasonable energy consumption. And the big takeaway from Groove is that clients freely and dynamically can choose this schedule irrespective of the backend. So they can choose a latency energy consumption trade-off that they see fit. For instance, if I want to go camping for a couple of days, I can put my phone on a slow mode, have a higher latency, but still be able to send messages and participate in the global anonymity set. To conclude, Groove is a communication system that hides metadata. It removes the rigid synchronous requirement of large-scale mixnet, and it better supports mobile devices compared to the related work because clients don't need to follow a global schedule, they don't need to be online at the same time, devices can go offline, so it enables a flexible energy usage. It has a reasonable bandwidth usage, and the latency is below 2 minutes. To be sure, there is still a lot of work to be done, but Groove brings multiple metadata-private communication systems closer to standard messaging apps. With this, I thank you for your attention, and I'm happy to take your questions.